Okay, so we'll continue on the last part of this kind of modern ASR technology, the language modeling part. Okay, so we'll do a little recap on connected word recognition. Again, it's basically practically based on bi-attribute decoding that we know, but it just has multiple HMMs. And there's a little component within the connected word recognition that involves a probability of the current word based on a past word sequence. So that particular probability needs to come from another model that gives that probability. So in order to take that into account to do the entire bi-attribute decoding, that particular probability is going to be generated from a language model. Okay. A particular language model that we'll talk about today is the Angren language model. So that's a very classic, also very standard language model that's being used in the modern ASR. So the method language model basically that wraps up the whole HMM, GMM based large scale continuous automatic speech recognition system. Okay, so depending on time, we'll do that and then the homework first. And depending on time, maybe I'll do a little bit of intro on the next time. If we have time at the end of the course, do the intro on where the deep learning, deep neural network comes into the play in the whole HMM, GMM based systems. Okay. So anyway, so connected word recognition. So you now know, ASR is built based on acoustic model features. Okay, the acoustic model is being built based on each word or each phonetic symbols. Okay, so when you try to recognize others essentially a sequence of words. Okay, given the others of T frames, you actually observe T MFCC observations. Okay, those are MFCCs are usually 39 coefficients, right? 13, 13, and 13, right? First order, second order, delta. You want to find a word sequence and maximize the probability of observation sequence, right? So thinking about this problem setup, right? You want to find the word sequence, right? Some sequence of some symbols, okay, and maximize the probability of using a set of observation. Okay, so this kind of a problem setup naturally is a bi-attribute decoding setup. Okay, so it's just now we're not decoding only on the phonetic state hidden state level. Okay, we're also decoding on the word transition and word state, this kind of sequences. Okay, so you have word, W1 to WQ, I put in candidate word sequence. Q is the number of words in time t. Then you find the most likely word sequence, right? Which word, okay, the number of words in time t, which word that is of the probability of OT given WQ. Okay, and the word sequence that maximizes this probability has this probability. Okay, the P of A maximize over all possible word sequence and the possible words. Okay, the probability of OT given the actual word sequence, right? So essentially, you have HMM, they're connected. You can find the most best sequence. You have each of the words being connected. You also are trying to find the most probable word sequence. Okay. That finding the most probable, the most likely sequence given the same observation. Okay. That's basically a bi-attribute decoding problem. So anyways, the problem setup now is this, right? You have OT is a T-frame observation, Q is just a word index, right? So it could be from word 1, 2, 3, and 4, and so on. So from T1 to capital T, the observation O1 to OT, we need to have an index tells, okay, which word that is coming from is most likely that word for that frame. Okay, so when we decode each of the, bi-attribute decoding, move one step at a time. For every step, you look through all the states. Right? So again, same thing here. So you move through one frame at a time. For every frame, you look through all the states. In this case, you look through all the states for all the HMM models, right? Each of the phoneme or each of the word has each acoustic model. So look through all the states, all the words, okay, and record, right? Record the probability for all the words of all those states, which large probability that is, and which word it could give me to that large probability, and store that for every word state for all the models. Okay, then you move on to the next time slide. Okay, and for next time slides, you have all the words, all the states. For all those words and all those states, you could count from one of them. You pick the one that's largest and keep it, right? And keep it, and then see where you have come from, and look through all of the six. Okay, so the process is similar. Right now, you just need to determine for every frame what's the largest probability for every word. Okay, so the rest of it is just like carrying out a bi-attribute decoding. So we define two additional probability terms. This is like the forward variables, right? Alpha sub t, I, b for each of the word for that state at that time, right? It's a max over all possible word sequence in the past. Probability of OT that now the current state is in I. For WT minus 1, all the past word sequence, and then now the current word is in particular vocabulary, right? The probability of A and T or V, given this a word at this time, what's the maximum probability, right? Again, max over all possible previous ones, okay. The current one that's largest is just sum over, for that particular word, if it have n states, you just sum it up, okay. So record that probability, okay. That will give you the largest one, okay. So again, so this is, the first one is a max probability over all past word, okay. So at this time, you always look at over all possible past state, past word, okay. And at this time, T, your state, right? That position is your state, given all past word and current word B. You compute that for every word, state of the word at every time, record the maximum probability at that time out of all possible in the past T. And here you just sum up those states for that particular word. Okay. So and again, you maximize over all past words. Okay. So look at what happens previously, now the current frame, and sum up all the states that correspond to this word. Okay. Sum up those probability and look at which of those past word probability give me the largest maximum probability of the current time for that word. And then you record that. Okay, you do it iteratively until you find hit the end and you backtrack. Right, you iteratively do that until you hit the end. Right, hit the end. At the end of the time, you look at which word at the end of the time out of all the words that you have. Right, for each of the words, you do sum up all the states. Right, because each word has multiple states. Okay, sum up all the states, sum it up, and see which one is the largest. And every time you record where you come from, so you can do it right away, going and backtrack to look at all the word sequences. Okay. So here are just some probability that you can initialize. Again, this kind of terminology is basically a bi-turbidity decoding terminology. Now it's just a probability you're computing, you're recording is P of A. Where does P of A come from? It comes from sum over I for all the state for that particular word, sum over all those for a particular time. So original bi-turbidity decoding that we learned in the past couple lectures for one HMN. Okay, we look at the best state sequences. Now, if each word has an HMN, okay, for every time frame, okay, you sum up all the state correspond to that word. Okay, that gives you this probability. Then you can record at which previous word that give me the largest one at the current time. Then you basically record it and do it for every word. Okay. Effectively, do it for every state. You sum up for every word and look at which one is the largest for a past word coming to this particular probability. Then you roll, right? So you got this tiered, right? First tier, you're doing that state level alpha T, alpha I of T. And then you do it at the second level with sum of the state for that particular word for each of the frame. And you roll your time until you hit the end. You backtrack. Okay, let's see the word sequence. That's how we do a thing. So it's not simply just it's an expansion on bi-turbidity decoding where now we just have multiple word sequence multiple word model put together. Okay, the only thing the caveat that here is because now we don't just have one HMN, where you have multiple HMN coming from multiple words. So for each of the frame, you not only have to decide whether you are in a current word of just switching state, or you have actually come from a probability, you actually come from some other word till this word that gives the largest probability. So at every frame, there are two options that can happen, right? One option is, okay, I sum up the states for this probability, that's one probability. I also can look at if I'm one of the last state, the other word jumped to my this beginning of this word. Okay, I need to look at which one is largest to keep supposedly the largest value at the current time, current state, okay, at the current word. Okay, so those possibilities you have to take into account. So like I said, you have to think about you now have multiple HMN. Each HMN has multiple states. But we're summing up those states to form a new probability. Those probabilities are the probability that we use to do bi-turbidity decoding. Okay. But that probability tells you the maximum probability given all past other possible word models until this point to do that transition. But when I'm coming from all the other models, there are two kind of ways that can come from. One is coming from the same model, same word model as your own the current model, or the model has been changed from other models to the current model, so the word state has changed. Okay, so we do make sure every frame for each word we do at this time we do make sure which probability is the largest, and we keep that. Okay, so that when we hit the end, you can backtrack to see the actual word sequence. Okay, so there are two separate cases. One is the cases where that particular time-based word probability stays in the same word, okay, or which one is largest, or the kind of time-based word probability if the current word is not the same as the previous word. Okay, so we need to pick which one is large to keep it as the maximum for this probability. So we ensure always every time, okay, for every word at that frame, okay, whatever probability we record as the largest probability of the transition from all previous word to the current word. Okay, so like I said, there are two types, right? So one case is simple. Basically, you have stayed in the same word, so nothing has changed. You're still computing this forward state-based kind of probability. For here, you should just sum up, look at all the transition from all the J's to the I state, VIV. Okay, the state in the same word under the same state times V, right? So it's the same V, okay, different state, okay. Somehow all past different state, you jump to the same state, you still compute this, okay. Or in other cases, you have actually switched to a different word. So A of TIV is not equal to the same, okay. So under the current word is not the same word as the previous word, okay. So that would happen, okay. That would happen if you are in the initial state for this particular word, okay. Out of all past words, right, max over all past words. There are 10 different words in your dictionary. If you have 2,000 words, max over that 2,000 words. If it's 10 words, then it's 10 words. Max over all the possible words. All those words has to be in their last final state. Okay, multiplied by some probability of all past words, right? Given the current word, right? So now you are in the new word given the past word, and that past word has to be in their final state. You look at out of all possible other words, which one is largest, multiplied by now you're in this word, then you're initially starting. Okay, so because transition can only happen, right? Because the ontology of HMN, the transition can only happen from somebody else's last state to the first state of my current model. Okay, so we can compute out of all possible other cases their last state jumping to the first case, okay, first state of my thing. So I want to look at which one is the largest, okay, to keep it for that particular frame. Okay, so because it could be switching or it could be staying. Okay, I need to make sure which one is the most large probability at that particular frame. Right here, basically, once you have those probabilities, you just sum it up, right? Sum up all the possible state transition and all the possible states within that particular model. And you look at whether this one is largest or this one is largest, right? Max over all possible other words, right? Their last state times some probability. This is just stay in the same word. Okay, you have made the transition, okay, into next time, but in the next time you still say the same words. You sum up the worst possible states here. So we want to every time frame you compute this and this to see which one is the largest. And you record which one is largest. Okay, where the index is. Okay, then continue on for every state for every time until you hit the end and you backtrack. Okay. And this is the probability. Now my current word is this given all past word. Okay, this probability we're later talk about. This is basically called the language model probability. The likelihood of me coming from the likelihood of me as this word, B word, coming from all other past words. Okay, so that's the probability of the natural language, right? I want to speak, right? You don't say I too want to speak, right? So there's very less likely you say in not grammatical manner, okay? More likely you say I want to do something, right? So there's a likelihood, right, of probability of me standing in this word given all past word. This is doesn't depend on the acoustic feature, right? There's no O in here, right? The O only happens in here, the alpha t minus 1. This alpha variable has observation, right? Depends on what you speak. Okay, so it depends on what you speak. This probably doesn't depend on what you speak. It depends on the actual word itself. Okay, that's what we call the language model. Okay, it doesn't depend on the host of T. Okay, anyways, at the end you get this thing. Okay, then you backtrack and you actually find all the word sequence and you actually able to perform the connected word recognition. So it's a tiered, more elaborate version of vector-read decoding. In essence, it's still doing vector-read decoding. It's just at every time step, when you try to decode on the word level, okay, that word level decoding you have to extra computing whether the final, like whether it could be staying the same state, same word state, or it has switched from other word model to the current word model that I have. And within that, that's where NLP, the language model, comes in. Okay, we'll talk about that today. How do we estimate this probability from words so that you can have additional model that gives you this probability so that you can put it together into do vector-read decoding when you do with this kind of large-scale speech recognition system. So if you don't care about this, right, okay, then it's a ASR system that purely based on what you speak. Okay? It doesn't care about the language. Okay? It doesn't care about the prior information on how the language should be. So that's why people call this thing prior knowledge, because there's a particular way we speak a particular language. Okay, that's independent of the sound you hear. Okay, just we speak like Chinese, the way we form the grammar, the way we form. There's a natural way that we speak. That doesn't depend on who you are, the way you speak, the sound of things, right? It's that kind of probability. If you care about that, okay, then this is important. Okay, this is also important because in every context you speak different language. Talk to your doctors, okay. Talk to your teacher, talk to your friends. You're speaking on the phone with your mom, okay. This kind of language model, right? The word usage that you have with different persons, they're very different. So this probability can be very context dependent. So a lot of time you see the ASR system eventually works quite well is because this probability is estimated very well. Okay, but then it doesn't generalize. Like you have a doctor patient use ASR system. It will work very poorly for friends conversation, okay? Because the word usage are very different. So that's what the language model is about. The rest of them, the Hindenburg model, we call it acoustic model, right? All those things we call it acoustic model because it depends on the sound, okay? The thing you hear, that signal you hear, the signal you record, okay? Extract features on the signal that you see and map to a certain set of phonetic symbols and using dictionary to come up with the words. Okay, so again, I want to bring the whole language model picture into this entire. So it helps in terms of the entire decoding of the connected word recognition. You want to actually rescore the probability of the transition by looking at the most probable prior knowledge of a particular language. Okay, in an ASR system. Okay, just keep that kind of knowledge in mind. Okay, so nowadays you can see, right, the very, very modern technology, right? If you are the very cutting edge, okay, the large language model can help to ASR because they can give you a very good probability estimation. Okay, so same thing, same process. Okay, because that's built on very large corpus. We're very sophisticated. The neural network give you the probability of the current word given password. Right, so it gives you that probability, then you can use that probability to help you re-decode the entire sentences as well. So the language model perspective in terms of automatic speech recognition system is basically built upon how likely my word transition would happen on that particular language. Okay, let me look at another PDF of our slide. This one. Okay. Okay, originally I had another slide. I think this slide talks a bit better, so I'll cover the language model based on this particular slides. Okay, again, a language model, not the pronunciation model. We'll skip the pronunciation model for this course, but the language model is more important than the language model. Okay, so I think we all know this, right? X feature vector, W word sequence, P of X given W, which is our HMM, right? We call it acoustic model. Now we need to know the word language model P of W. Okay, so basically what does a language model? It basically tells you how frequent a word occurs. Okay, how frequent a sequence of word occurs. That's basically practically the essence of a language model. Okay. All right, so again, this is the fundamental questions, right? Argmax W over a set of all the vocabularies we have, the language model multiplied by acoustic model, right? This is the prior probability over words, we call it language model. This is called the probability of feature given word, okay? Given if this particular word, the way you sound it like that, okay, that's your observation. And this language model gives you the prior probability of word, we call it P of W, P of X to the W. Okay, so again, that's it. So it helps a certain way, right? Look at this. This is our room for a 4-hour period, right? So again, this is our room for a 4-hour period. Okay, again, these two sound almost exactly the same. If you look at acoustic model, they may give you almost exactly the same probability. But you can look at it and say, okay, this is nonsense, right? You don't have it. This is our room. There's no word called our room, right? It should be this our room. Okay, so the sound can be ambiguous, okay, but the language is not, okay. In the language, you don't see this thing, you do see this thing. So if you have a prior knowledge on how the language should form, okay, you will easily pick this one over this one as you do that transitional decoding, right? Finding the most probable word sequence. At this point, you will keep here, not this one, okay. So this is how the language model do things, right? It is easy to recognize speech. It is easy to recognize pitch. Okay, again, sound very similar. Okay, in terms of language model, it probably helps you to say that it's this one, not this one. Okay, you don't usually say this one, right? So language model give you a sense of how usually, okay, you will speak a particular language using those words. Okay, so maybe in some context you see this, right? But most of the time, right, you probably will say things like it's easy to recognize speech. Okay, not it is easy to recognize speech. Okay, but those two can sound almost equally the same. Okay, very likely to be confused. Okay, so language model really helps you solve this issue because acoustic model coming from the way the signal sounds. Okay, language model has a prior decoding from things that's unlikely or likely. Okay, so again, language model, the goal assign high probability to good stuff, right? Meaning things are more likely. Okay, save the well, save the date, save the well, date, bait, right? So assign low probability to the bad stuff. So basically, you can imagine language model is provide a restricted access to acoustic model. Because acoustic model can say, okay, all these things sound the same. All those things are equally likely to appear if I just recognize my speech based on the acoustics, okay? But language model will kill some of the probability off because those are not the kind of sentences you will speak in natural day or daily life. You give a very low probability to those. So as you do most probable by attributing, those probability will be very low. Then you won't go through those word states, okay? And those words that get regarded, okay? Then you get a better form, okay, ASR system. Okay, so you can imagine language models providing restricted access to. Anyway, so we'll continue. So the very restricted access to acoustic model. Okay. So let's do this. Okay, so N-gram model is the one that's the most popular and most widely used, and it's very straightforward. Okay, and if you run an ASR system using N-gram model, it usually works fairly okay already. Okay. So again, the goal is find a probability distribution over word sequence, right? Probability of word essentially just find a probability of disjoint probability of W1 all the way to Wn. Okay. So what type of model was the simplest model we can do? Okay. You can say this kind of a first order Markov. Okay. So every word it only depends on one password. Okay. We call it first order Markov. That's basically we call it bigram language model. So P of W1 all the way to Wn equals to just probability of W2 given W1. probably a W3 given W2. Okay, so it's a first order Markov like the hidden Markov model. And the hidden Markov model say, okay, my transition only depends on previous state. Okay, you can say the entire, the entire word model. Okay, joint distribution only depends on every word only depends on its own password. Okay, the one previous password. Okay, so some of the art problem, this kind of thing, right? So it either stays in here or it has leaves that. Okay, so look at this. This is a first order Markov plot where you can rewrite the probability of word sequence instead of just bigram probability. Okay, so repeat, right? So if you have a sentence called 1, 3, 2, okay, so the language model is trying to assign probability to this word sequence, probability of 1, 3, 2. How do we do this? If we follow, we call it n-gram, bigram, right? Bi means the n, right? N equals 2. So when n equals 2 equals a bigram model, this particular probability becomes the probability of 1 given start, okay, 3 given 1, okay, 2 given 3, and n given 2, right? So you have 1 given start, 1 given start is 0.3, right? You have 3 given 1, okay, 3 given 1, so that's 0.4 right here, okay. And then 2 given 3, and 2 given 3, 2 given 3, 2 given 3 is here 0.2, okay, then you have all these three things multiplied and 0.024. It's very simple. This particular three-word joint probability now become a just factorized into one conditional probability, and three of them multiplied together gives you this probability. Okay. Right here, right? P of 1, 3, 2 equals P of 1, P of 3 given 1, P of 2 given 3. Okay, so the n-gram model looks like this, right? P of W given to WL in particular sentences, okay. That equals probably a 1 given L, P of the current word given the last word, okay. Depending on how many last words you give it to, okay. If it's one last word, we call it bigram, okay. If it's two last words, we call it trigram, okay. If you have multiple words, then you have, then you continue, okay. So quadruple, right? So those type of things. So the joint probability given a word sequence being factors into conditional probability. Okay, so those are basically the major assumption behind the n-gram language model. Okay, so the current word only depends on one password, or the current word only depends on two passwords. Okay, as long as we can compute this probability, then we can actually find a language this probability to approximate this joint distribution. Okay, so it's probably based on the n-gram language model. Okay, now you need to train it, all right? Again, this probability, right? Like in the Markov model, transition probability, you don't know, right? You don't know this probability. You need to train this n-gram language model. Okay? You just form a n-gram language model, say my joint distribution will factor into first order Markov, okay? or second order Markov. Okay? Now you need to actually know this probability. So where you get this probability, you actually get it from training data. Okay? So what training data we usually give is essentially a bunch of words. Okay, so it can be disjoint from the speech data as your training data. Right? Usually the training data for language model are gathered from other places where you have a lot of text. For example, newspaper. Okay, for example, online. Okay, there are a lot of articles. Okay. Those things will give you estimate of the probability. Okay, it doesn't have to come from the speech data. You collect the thing. Okay, so training the acoustic model requires speech data and transcription. Training language model only requires text. Okay, so you only need to look at the text data to be able to train your language model. So language model usually come from some other sentence. Like I want to fly from Austin to Boston. Can I get a vegetarian meal? Basically, you get a million kind of these utterances, and you can start doing an estimation. Okay. So, question, right? Our AMs, our acoustic model are usually trained with more data, and the question is obvious. Language model usually trained with more data because they're easy to get. Okay, you just basically look at all the newspaper, all the online, all the books, whatever things you can get a text based off of these things, then you can use it to train this language model. And that's why recently, all these ChatGPT, they start with text, okay? Because those are the data that's most easily you can scrap and train. those things are essentially a language model. Okay, this is a particular version of language model where we simplify that joint probability of the word sequence into a first order or second order Markov probability multiplication. Okay, so for sentences, you add a beginning of sentence token, okay, and then also predict the end of sentence token at the end. Okay, so probability of W1 to WL now becomes I to L plus 1 because it had one more token, okay, P of WI given WI. Okay, so when we compute the probability I'm going to, it should be the probability of I'm given is the first word multiplied by going given the previous words I'm multiplied by the probability of 2 when going multiplied by probability of this end given the previous word is 2. So we also usually in the training analysis we add the beginning token and the ending token. So how do we estimate a particular set of migrant probability? So how do we know probability of fly given 2? Okay, what's that probability? Okay. So you look at your training data, it's very easy. The probability of fly given 2, you just look at the total counts of these two happen together given divided by the total count this thing occurred. Okay, so they give you an estimate of out of all the times you see TO, how many times you see 2 and fly together. Okay, this gives you this conditional probability. Very straightforward, and this kind of estimation, it is maximal likelihood estimation. Okay, it gives you the maximum data likelihood. Okay, under this Bayesian language model. So P of MLE of WI given WI is just a count of number of times these two words happen together divided by sum over all the words count of this. Right, so basically count of WI minus 1 WI divided by count of WI minus 1. So in this case, right, probability of fly 2, you just need to look at the total count of 2, and total count of this thing happens out of, say, 1 million sentences that you see in your corpus. And you repeat that for every pair of words, right? So if you have, 100 words, you have 102 square thing combinations. Okay, you have to look through all these counts. Okay, and then basically it's essentially a counting business. Okay, just count. Okay. Write a program that count really fast, so we can count all these things happen together, count this thing happen, and then you subdivide and you get this MLES. That's good. Okay. Alright, so there's a corpus called Wall Street Journal text that's one of the very standard beginning of the ASR data set that people use to train language model. There are 23 million words, right? It's basically from Wall Street Journal. We just gather all those past times that people write Wall Street Journal, all those texts, right? So Federal Home Loan Mortgage Corporation dash $1.5 billion of real estate. You see there's some tricks here. I won't go into detail, but you can see that. Usually in an actual newspaper, you don't write 1.5, you just write 1.5, right? The numerical, right? But you have to always normalize this, okay? So that the numerical 1.5, when you write 1.5, they should be the same thing, okay? So you, and then when you say 1.5, maybe you say the point, okay? In the text, you don't say the point, you just write the point, okay? So you write point, okay? So there are some tricks, right? So the program that you have comma, and we say this is comma, right? This is one token. So there's some normalization of the token we need to do for NLP. Okay, so it's a natural language processing sort of the techniques and to normalize the text so that we can do counting, right? We can look at each of the sentences. We can look at national laboratory. Okay, now we just count number of times national laboratory occurred, divided by number of times national occur, then we have the background probability of laboratory given national. You just basically look through all your sentences, look at all possible combinations of all the words, okay, and see number of times these two occur, divided by number of times the previous word. Okay, then if you have trigram, it's very easy, right? National laboratory comma. This is a trigram, so you look at these three occur, right? then you look at this thing occurred divided by this thing. Okay, so that's basically how you do trigram probability. Okay, so and then if you want to extend it, it's 4 gram, 5 gram, 6 gram. Okay, the same business. Okay, you just need to extend the number of count and divide by number of times this thing coming out from that word. Okay, all this boils down to counting business. So here's an example, right? Probability I hate to wash. Probability, the second one is I hate to wait, right? So I hate to wait. The second is I hate to wait, right? So we can look at the language model for each one of them and see which one is most likely, right? You assign the most probable thing to your language model. So again, then you can collect all the bigram counts and unigram counts. Okay, then you get this kind of a probability table. I and starting together, there are 3 times. I and this beginning of things started together 3,000 times. Okay, so basically you do this counting for everything. Okay. Look at this. Usually you see this can be quite a sparse matrix. Okay, some of this will have nothing, right? 2i, right? I coming from previous in this corpus, it has 0 count. Okay, this could happen. Okay. So, but and then in a regular training, it's basically you go through the databases, you collect your bigram counts, unigram counts, then you normalize it, so then you can compute this probability of I hate to wait. And probability of I hate to wait, right? So you have 3,234 divided by 89,000, right? So that's this thing. Starting, right? There's 89,000 sentences, so always have a starting. Okay. I given the previous one is starting. There are 3,000 of them. So I as the first word within a sentences, right? That probability is 3,002 divided by 89,000. Okay, and then you so on, right? You once collect all these bigram counts, okay, within your training corpus, you can start computing all this probability, and you just multiply them through, you get this probability. Okay. Sometimes you place a log, okay, in the front to make them into summation so that it doesn't, goes below the precision, okay, because usually our computer has a finite precision. Okay? This multiplication probably can get very small at some time. Okay, but that's just implementation. The probability I hate to wait, right? And again, I as the first word in the sentences, we can look back, right? It's 3, right? 3. So 3 out of all this has to probability. Okay, that's a very small probability. Okay, this thing, and then probability of hate given the previous word is I. Okay, there's 0 count, so it has 0. So you don't have to do anything. Then the rest of it has to be 0. So this probability is going to be 0. Okay. So this is under this corpus of 89,000 sentences. Okay. The probability of I hate to watch that language model. If we use bigram as our assumption, that probability is this. Okay. If you use bigram as assumption under this training corpus, the probability of using I hate to wait. Okay, that probability is 0. Okay. So a very straightforward exercise of your training language model, assuming a bigram, okay, n equals 2, bigram, given a training corpus, start counting. Once you finish counting, the probability is here, okay. Then you look at this thing, right? So this is the probability that we see in the connected word recognition, P of V given WQ. Okay, if it only depends on one previous word, you need to multiply by this. Okay, so that's if you hate the previous word, is a hate that's given in the same model. If it's hate given all the other 23, meaning -1 words of not the same word as hate, you can compute this probably over all the rest of them and then look at which one is the largest and then you keep that as the most likely one. Okay, so it's very elaborate, it's very large, but conceptually it's very simple. Okay, just need to compute all this probability and record and do things. Okay, what's better than the first order bigram? Okay, you can do a trigram, right? Probability of 2 given 1, 2. Okay, so if you don't depend on just one previous word, depend on 2 previous words, and we call them trigram. Right? So, for example, here, okay, bigram probably the same I n, then will become probably the same given starting, I given sin, n given I, and ending given n, right? Then you have this thing. Okay. the probability of trigram same given then because then becomes same given it's the two previous starting tokens and I with the starting and the same probability of n given same and I and probability of any point I and n. Okay, so if you want to find the probability of n given Sam and I, okay, you just look at the count of Sam, I, and this thing occurs divided by the count of Sam and I happen together for your sentences. Okay, so again, this exercise of extending from bigram to trigram is very easy. Okay, you just that conditional probability has one more word in the previous one. Okay, that conditional probability. And to do estimate of this conditional probability, you just do counting. Okay, the counting now just have to count 3 words divided by 2 words. Previous is 2 words divided by 1 word. If it's unigram, then it's just that single word, right? Divided by the total number of words. Right? Count the total number of words of that word happening. Okay, so again, this kind of thing we call Markov model order 2, and it's trigram. Okay, trigram. So the probability of the current word, it depends on the last 2 words. Okay, the probability of wi given wi minus 1, wi minus 2, wi minus 1 is just this count. So again, think back in our connected word recognition, probability of v given all passwords. Okay, if that probability of v current word given all password has been simplified to given 1 password, that's bigram model. Here's my probability of this current word given past 2 words. Okay, it's been simplified. Now all passwords now become only past 2 words. That we call the bigram language model. Okay, so you can get that probability from training a bigram language model or a trigram language model on a large training corpus. Then stick that probability into your ASR system so that it performs spectral decoding using the probability you give it to. Okay, recap. This Ingram model, very easy. Okay, conceptually easy as well. It simplifies a lot of assumptions. Okay, so Markov model of order n-1 can predict the current word from the last n-1 word. Okay, right? Predict this word based on the past 2 words, right? The probability of this word given the past 2 words. Give you that probability. If you think about this, right, like I said, when we're coming from a automatic speech recognition system, looking at the current days, the most hardest ChatGPT, right? What they're doing the next word prediction based on the past word. It's just that they don't rely only on 2 words. They rely on past million words, right? The token can be in the billion size. Okay, so the network has become so large, the data has become so large, so the next word prediction can depend on very large corpus of very long history. Okay, that's where the current modern language model have been doing. Okay, and then in the past, that's what's been done in a speech recognition system as well. You just because of data issue, you only go back to 1 or 2 last words. Okay. When you train the model, get a corpus, don't forget the others beginning and the end. Okay, so because every word can be a starting of the sentences. Okay, you need to keep that tag so that the system knows the probability that it is a starting of the sentences. And like I say, very easy to train. Okay, think about it. If you don't know any theoretical foundations of this thing, okay, it doesn't even matter, right? You just get a large corpus, decide how many words you want to do, and start. The rest then is counting. Okay, once you count, normalize. That's all that's involved in terms of maximum level estimation. Okay, there's no elaborate expectation maximization, all this very fancy math in terms of learning a probability. All you need to do is count and normalize. Okay, that's in terms of learning. That's a very easy. Okay, there's nothing specific about that. Okay, NOE estimation. Okay, very easy. Intuitively, very easy to understand. In terms of implementation, very easy to implement. Okay, we just need to go on and grab data. Okay, now as we know, things never go so smoothly. Okay, always problem comes about when we think about this kind of issue. Okay, so the problem is this. Think about this sentence: the world will end in 2038. Okay, what if the count of 2030 equal to 0? Okay, so any one of these triger count, as long as it's 0, okay, then this particular probability, okay, this sentence probability will become 0. Okay, so is it really it's not happening, or is it just that you don't see in your training corpus? Okay. Now, for most parts, because you don't see that in your training corpus, you don't have enough training corpus to cover every possible way people can use language.
right? So we can of course say this sentence is perfectly normal in our sentences. But you go on using your Wall Street Journal as your training corpus to try to train a trigram language model. This thing just never occurred. Okay, when it never occurs, it's zero. When zero and then at decoding, it's always zero. So I think that's basically the largest problem with the n-gram language model. Okay? There are just some gram that you just don't see. Okay, but if you look at it, they seem to make sense. Somebody will say it. Maybe not very likely, but somebody will say this. Okay, so how then we can start designing called smoothing algorithm. Okay, so we still try to assign high probability to good stuff. Okay, we also want to assign some probability to some unlikely stuff that originally have zero counts. That's an issue. Okay. So let's first look at how bad is the zero count problem. Okay, in say for example Wall Street Journal, there are 11.8 million words. Okay, say that's held out a part of that Wall Street Journal data as things that you don't see in your training, and then particularly as a validation. You can count what's the percentage of fractions of trigrams actually not seen in a training corpus. Okay, the answer is about 36%. Okay, so again, in the 11 million word corpus, okay, you take a subportion out, you do a trigram, a simple 3-word happening together count. Okay, now there are about 37% of this kind of trigram never actually appear in your training corpus. That does appear in your held out data sets. So that means, if you rely completely on this training corpus to do your language model, and think about a language model give you that probability of V given WQ. That V of WQ, you're going to insert it back to your connected word recognition. Okay, so for certain words, it's going to directly give you a 0. Okay, when you give it a 0, even if you actually say those words, it'll still force it to be 0. Okay, so that's a problem with the n-gram language model, because you give 0 to somebody. Okay. And we'll give it to 0, then your system will never ever be able to decode those words. Even they're unlikely, or sometimes people do say it, it's just never possible to decode those words because it's assigned to 0. Okay, so that's a problem. And look at the severity of the problem. Almost close to 40% of the same trigram in hello set that's never seen in a training set. Okay, so think about it, about 40% of those things that will actually never get decoded. So that's a fairly complicated issue. Okay. So let's continue. Okay. So that's the problem with learning, right? So we're doing a data-driven learning. Everything is based on maximum data likelihood estimation, right? So that's what will happen. Like in theory, maximum likelihood estimation is as good as it gets. Okay, if you have a lot of data, right? But if you don't have a lot of data, because it is finding a parameter that maximize the data you see. Okay, so if you don't see enough data, even those parameters that maximize the data likelihood you see, those are bad parameters. Okay, so that's a problem here. In practice, right, when the data is sparse, okay, bad for n-grams with 0 or low counts. So these kind of n-gram models are very sparse. Okay, there are lots of grams that you just don't see. Okay, when you don't see them, the probability is 0. Okay, so when you do a maximum estimation, those probabilities are 0. Okay, so this becomes a very, let's say, a paradox. Okay, you're in a situation where MLE, in theory, give you the optimal parameter. In practice, it doesn't work. Okay, so you have to somewhat work out, some ways to rearrange your probability so that it works, but they no longer follow MLE. Okay, so that's where engineering comes about, right? So you kind of start playing a lot of different tricks. I'll show a few tricks that that the n-gram model plays, but none of them is optimal. Okay, because the most optimal is MLE, because it gives you design a function, it gives you the actual point where it actually maximizes some functions. But we know if you do that, it actually gives you bad results. Okay, so this kind of language model is I always think it's quite interesting, because you don't get a good estimate by doing MLE. You have to do some ad hoc sort of tweaking to make sure it actually works. Okay, so we'll start doing some stuff. Okay, training set, again, repeat. Okay, it's from Wall Street Journal, 11.8 words. Okay, test set is also 11.8 million words of Wall Street Journal. Okay, so let's assume if the trigram has one count in training set, how many counts does it have on average in a test set? Okay, so that's 0.22. Okay, so the MLE is off by a factor of 5. So again, you have this training set, okay, testing set, okay, test set never see, training set is C and C. You start counting all the trigrams, all those 3 words connected, count all the 3 words, okay. Look at all those pairs that give you 1 count, okay. And look at all those counts, okay. Right, you have 1 count in training. All those pairs of words, you look at them in the testing set. On average, only appears, right? It's on average, right? Over all the sentences in the testing, it's about 0.22. So again, even if you count them 1 time, okay, have 1 count, okay, actually about 5 times more likely than the true test set. Okay, so here then people start putting a trick here. So MLE is the frequency of n-grain training set. Okay, the goal is here trying to estimate the frequency of n-grain in the test set. Okay, right? So because there's a mismatch. Okay, the mismatch is where once you train, you get it out on the world and then try to really test it. The counts, the probability counts are actually quite off. Okay, so we call our techniques a lot called smoothing or called regularization. You're trying to actually adjust MLE estimate to better match the testing data. Okay, how to smooth? Okay, many ways to smooth. Okay, let's start very simple. Okay, let's first think about a unigram. Okay, the probability of each of the word happening, right? 1, 2, 3, 4, 5, 6, 7, 8, right? Assume you have database, you have word 1 count 5 times, 2 count 2 times, word count 2 times, 1 times. MLE estimate will be 0.2, 0.5, 0.2, 0.1. Okay, sum up to 1. All these words will never be able to decode because you don't see in your training corpus the MLE estimate is not very good. Okay, so all these are sparse. Okay. So let's say MLE estimate of a unigram language model here. Okay, the basic idea behind smoothing, okay, is basically trying to adjust the probability of words with 0 counts on average. So how do we adjust the probability of words with non-zero counts? So because all the probability sums up to 1, right? Imagine here, right? All these probability sums up to 1, okay? We're gonna adjust this probability, but they still need to sum up to 1. So when you try to say, okay, all this 0 count has to have some probability, that means this has to be somewhat lowered, okay? So that the total probability still needs to be summed up to 1. Okay, so now it's a matter of how we move some of the count here, some of the probability mass here to here. Right, all those things are called smoothing. Okay, making sure there are no zeros here, but because they all need to sum up to 1, so what happens is you have to take some part of this thing into here. So in Chinese, 我们通常讲这个是劫富济贫。Okay, so for some count 就是一堆 mass 在上面。Okay, 但是加起来是1，那你那些是0的话，你只要给它1点，怎么给？你加起来只要是1饼是一样的。我要丢1点给没有钱的人，我就是势必从有钱人身上挖过去。Okay, 那我要怎么做这件事情 ？It's called smoothing. Okay, in general language models, what they're doing as well. Sum of the 1, you get some part of the mass from the rich to those very low counts. Okay. The very simple one is called a +1 or +1 smoothing. Okay, it's very simple. Okay, so if you have say 9 words here, this original count, these are the POE estimate. Okay, you simply add 1 counts for everybody artificially. Okay, give everybody $1. So no person has $0. So everybody has $1, and then for the rich people, we also have $1 extra. Okay, so you look at this probability now. 0.3, 0.15, 0.0, and 0.05, 0.05. It still sums up to 1. Okay, you have some probability here. You drastically change the probability here. Right? Think about this from 50% all the way back now to 30%. Okay, you give them $1 each equally. Okay, but effectively in terms of probability, it drops a lot. Okay, so it's a very crude estimate. Okay, works to the point where there's no 0 count, but the problem is you kind of take away too much, okay, of the originally very good stuff, right? Because when we do MLE, we assume it works well because the thing you have seen a lot, that should give you the good estimate, okay? The thing you don't see a lot, that's the probability to have a good estimate, okay? But now you actually take away the part where you're actually seeing a lot of of the 1, okay, then maybe it's 50% not a bad number, okay, but we now drop it to 30 just because of this add 1 smoothing, okay. So this add 1 smoothing is okay, but no, it's not very good, okay. So it's very sensitive to how much you add, how to set, okay. Does it discount low and high counts correctly? Is there a more principal way of doing this? Okay. Now the first thing that's been introduced back in the 50s, we call good Turing estimate. Okay, assuming you have train set and test of equal size. Okay, the total count of mass of k plus 1 counts in the training equals the total count of mass of k counts in the testing. Okay, so it's a very simple switch. Okay, to say, okay, for all the probability mass that assign to say 2 counts, okay, k plus 1, okay, k equals 1, okay, 2 counts in the training, that equals to 1 counts in the testing. For the total probability, okay, for the probability assigned to 1 count, so k equals 0, that equals to the total count of mass of 0 count in the test set, okay, right? So again, it's very simple as that. Okay, so all the count in the count of mass of k plus 1 words in the training will equal to total count of k counts word in the testing. We call it good Turing discount. Okay, you still basically assigning low probability things to low probability things, right? But then you get rid of the 0 count problem. Okay, right? So you don't just add 1 to everybody. You say this equal to this mass equal to this mass, this mass equal to this mass, this mass equal to this mass. But originally they only have 0 and 1 count anyways. Okay, those are rare events anyway. So you give rare events the same kind of probability max. Okay, so it seems to be more principle. Okay, you don't have to worry too much about I'm shifting the 4, 5, 6 count with the 1 count. Okay, because they are not in the same level. When you see some trigram counts over 10 times. You should have a very good MLE estimate there. Okay, good Turing discount would say, okay, if you already are low counts, okay, just share among yourself. Okay, if you are high counts, okay, share among yourself. Okay, so that's how they get rid of this kind of 0 count problem. So there's no longer getting from the rich to the poor, right? Because you're basically shuffling between the poor and shuffling between the rich. Okay, so you don't change the overall shape of the probability mass distribution that much. Okay, so it's one way we call the good Turing estimate. So the total count of mass of 1 count of trigram in training is equal to total count of 0 count. Okay, trigram in the testing. Okay, so the training, if you have 4.32 million 1 count trigram, okay, so that's equals to 4.32 of NC test counts. Okay. So the 10 sets train test set, okay, there's a 11.8 million words, and you have this divided by that, that's 36.6%. Okay, so again, so the P, originally the MLE estimate, right, C count divided by the total count, that's your original MLE estimate. The smooth probability then equals the smooth count divided by the total word count. The smooth count, right, equals the number of words with k plus 1 counts multiplied by k plus 1 divided by number of words with k counts, right? So basically you reshuffle the number of counts now you have for k counts, right? So it equals to the number of k plus 1 counts times k plus 1 divided by number of words with k counts. Okay, then this number becomes the new smooth counts divided by the total counts. So basically, it's a switching between, because the count will detect how many masses you have sitting on that number of trigram count. So basically, you're swapping between those masses. Okay, here is an actual estimate. So this is an actual probability, right? In the blue line in the test set, okay, across training set counts, right? 0 count, 10 counts, 20 count, 30 counts. Okay. And then if you look at the average test set count with your good Turing estimate, look at it fits quite okay from the set when you hit larger counts. And when you see larger count here, the actual is actually a smooth here. the good Turing estimate start to jump around, because good Turing estimate is good for low counts. Right? And the low counts probability they fits well because it shuffles around rare events. Okay, so and then get rid of and those rare events should have kind of the similar rare occurrences. Okay, in the original MLE, the rare events have no good estimate because you don't see them enough times. Okay, you don't see them enough times, so you cannot get a very good 0.0001 estimate. Okay, you don't have that. But if all of them are very rare events, you just share those counts as fits line well. But if you see, look at this, over 25 counts. Okay, almost 30 counts. Those are events you see quite often already. You have a trigram that's appeared 30 times. Okay, that's a very important trigram. Okay, but then if you use good Turing estimate trying to reshuffle them, okay, again the estimate will start to get off. Okay, from them. So good Turing estimate is good for rare events, especially 0, 1, 2 count those things. But again, it helps you solve in a principal manner. Okay, of the plus one smoothing issue. The plus one smoothing issue. It works, it always works. It's just because the trigram are too sparse, right? If you add one count to those things, right, go from 0 to 1, then you practically lower the probability of the high frequency event too much, okay? Good Turing estimate is just saying, okay, my counts of my 1 counts in the training equals to count of my 0 count in that same event, okay? When you do that equation, okay, then what you're doing is you're shifting the probability maximum again within the lower count ranges, and also making sure there's no 0 count. Okay. Also making sure those rare events stay as rare events. Okay. The high probable events still stay as high probable events. Okay. So good Turing is very good. It works quite well. I think now even into the 21st century, I still people are still doing some version of good Turing estimate to do a language model, because a very nice trick, awesome way to smoothing unigram models. Okay, works for counts with large number of counts. Okay, do these things. Okay, so that's unigram. I will talk about unigram. 1, 2, 3, 4, 5. So let enough counts. I give it more counts. Okay, now you have, or if you have this kind of n-gram issue, bigram, trigram kind of stuff. How do we apply this kind of good Turing stuff to bigrams? Okay, there are two kind of ideas, right? You say, okay, I treat bigram as like another unigram. Okay, you pull all bigrams together, computing good Turing discount, and you use smooth counts to estimate probability. Or you just apply good Turing independent to each bigram distribution. Okay, so which idea makes more sense? Can we do better? Okay, so again, consider a single trigram distribution probability of Wi given Antonio, right? So the count of Antonio equals to 0, the count of Antonio Theodora equals to 0. This probability of good Turing estimate given Antonio equals to probability of good Turing Theodora given Antonio. Okay, so that's basically what we're saying here, right? If you have bigram, they both have the same 0 count. Okay, in a unigram, if you apply good Turing estimate, we say they're the same thing. Okay, they will share the tested bigram 0. This is one, say this 0 count, so 1 count in a training bigram, okay, of the mass. But that doesn't quite make sense, okay, because if you look at this bigram, intuitively probably this probably will be greater than the other one, okay, because but then if you just treat them as another unigram, okay, and then do the same discounting of moving masses, okay, these two will be put in the same category as they move the masses. Okay, so intuitively it doesn't seem to make sense. Okay, so there are other ways we can try to do it. I like them how to say this show a pie, right? Because whatever you do, there's always one pie you're slicing. It just depends on how you slice it. Okay. Okay, so instead of assigning probability to unseen trigram uniformly, you assign proportionally to the unigram distribution of P of Wi. Okay, so it gives more mass to the than to Theodora. Okay, so probability of this kind of smooth Wi given Wi minus 1 will be equal to probably good Turing estimate of P of Wi given Wi minus 1 if the count is enough greater than 0. Otherwise, okay, it goes to some constant, okay, alpha of Wi minus 1 times the unigram counts of the previous words. Okay, This kind of approach called a back-off approach. Okay, when your bigram has zero count, you don't actually look at the probability in terms of bigram. You look at the probability in terms of the unigram. Okay, so what happens in this particular words? Okay, and then that depends also on some constants of the other wi minus one. Okay, so you don't count bigram. Okay, if that bigram is zero, okay, you don't say I'm going to perform good Turing estimate to reshape that probability in terms of bigram. I just directly back off, okay, to unigram. Okay, if this particular unigram, okay, P of wi also zero count, what do then you do good Turing estimate? Okay, so good Turing estimate operate on unigram. Okay, when you're in a bigram, you do bigram. When you don't have bigram, you do unigram. When you don't have unigram, you do good Turing estimate. Okay, so kind of a don't do the good Turing estimate directly on the kind of a bigram things. Okay, so unseen bigram will map to smooth unigram. Okay, and the rest of them are the seen bigram will be stuck into here. Okay, so that's what again you still have one pi to show the probability of mass one. Okay, so that's what people usually do. So always, there's a cap. Okay, this is probably a max. Okay, you just need to swap. Okay, there's a set unseen bigram you map into smooth unigram. Okay, the seen bigram is just the rest. Okay, so we can put this all together. Okay, so good Turing estimate, back off. Okay, and finally put together we call the CAD smoothing. Okay, 1987. Okay, so what happens here is you give a good thing to each one of them. Okay, so if a particular gram, okay, the count is high enough, let's not do anything. Just take the MLE estimate. Okay, if the say we have a bigram language model. If I see count over 10 counts or 20 counts of a particular bigram, then we just use the actual MLE estimate, okay, which is quite good. Okay, then if it's between some low counts, right, 0 to 8 or 0 to 10, okay, then maybe here we can use some good Turing estimate on the bigram. Okay, then when you hit 0 counts, then we back off, okay, to a unigram. And if that's zero gram, no unigram, then you back out to the unigram good Turing estimate. Okay, then basically it captures all the good things about everything, right? So if you have a count, okay, of some symbols of word, that happens a lot of time in training corpus, just directly use your MLE. If you don't see enough times, but there you do see a few times, okay, then you try to swap among those few times, right? You do good Turing estimate of those bigram. So good Turing estimates basically say, okay, all the k plus 1 equals to k. Okay, so basically you swap, basically minus 1 of the counts. Okay, so you're swapping that frequency with the nearby counts. Okay, so between 1 to say, this empirical usually set between 10 or 20. Between those ranges, then those probability counts use good Turing because then you swap among the low count population. When you hit 0 bigram counts, you don't just stop there. You say, okay, if I'm 0 count, I will back off to unigram because unigram some scalar depend on unigram. Okay, because unigram like that, right? The is definitely more likely than Theodore. So you want to place a little more probability to the Antonio where the previous one is given not the Antonio where the previous one is given Theodore. Okay, so when you look at the unigram probability of the will be much larger than unigram probability of the Theodore. Okay, so it depends on some weighting constant of that back off to the unigram. Then all these things together, of course, all these things has sum up to 1. Okay, so again, still you're slicing a single pie. Okay, you just said for those people that have enough counts, don't touch them. For those people that have few but some counts, okay, do good Turing estimate to maybe swap them a little bit. For those people that just have no counts, back off. Okay, to the lower order gram. Okay, this thing can extend it to bigram, trigram as well. Okay, it's the same kind of process. If you see you do a trigram language model. You see some trigram that happens a lot, then keep it. Okay, for those trigram that sits in the middle, you do this Quaternion estimate. For those trigram you don't see things, back off. Okay, background. And if backgrounds don't see anything, back off again to unit ground until you hit the end. Okay, so if you really never see that unit ground, nothing happens, then you use good Turing estimate on those zero count unit ground. Okay, so again, these are CAD smoothing I think it's on the Wall Street Journal. One of the example here. Okay, so PLE estimate is this thing. Okay, and the PLE smooth. Okay, if you look at them, it's a bit better match because I think above 20, right? In this case, they almost stay the same, right? If you had count 40, they're probably the same among this range. Okay, it doesn't change too much. They're swapping in the middle. Okay, when they're very low probabilities, okay, they remain very low. Okay, for those things that have complete zero count, yet it's not impossible to decode them, but they have very less probability. Okay, but all these things still sums up to 1. Okay, so this kind of probability smoothing, okay, CAD smoothing is maintain the largest. Okay, shuffle around the middle, assign very low probability among the low, okay, to give it a little bit of weight so that it's not impossible to decode this thing, although it's unlikely that it's going to be decoded. So the only way that this can be decoded is when your acoustic model really says this is error, okay, nothing else. Okay, so there's no other way. You have very low probability that will occur, then your ASR will actually output an error. But it's at least it's better than you are never able to decode error. If it's 0, then you're never able to decode. And this probability maintains, right? 2 is a very natural, frequently occurring word in our sentences. They remain at the same probability of 16%. So you don't take away too much of probability of this word 2. And that happens quite a lot in our natural language, spoken language as well. So again, this is just an example. Okay. So some recap. Okay, the MLE estimates usually way off for low counts. Okay, 0 probability it kills off performance. Okay, so key aspects of smoothing algorithm: how to discount counts of unseen words, how to discount counts of seen words, estimate the mass of unseen words, and back off or get information from the lower order models, right? So again, these are 3 basic techniques in terms of smoothing, right? So 1, for all the words I've seen, okay, how do I discount some of the words? Basically, imagine them as money, right? Discount, then take away some of the money from those people that have counts. Taking away that's fair. Fair meaning a higher probability counts maintain high probability. Lower probability counts still maintain low probability counts. Okay, but you take away some of those, because once you take away some of those, you can assign those counts to the 0 count. So those 0 count trigrams will have some count, okay, because of when you take some part of it out from that thing. Okay, so let's go discount. Okay, so we can estimate a maximum C probability. Last one is when we have this Markov order model, trigram can back out to bigram, bigram can back out to unigram, unigram then back out to complete estimate of unseen words. Like they say here, the CAD smoothing really standard in academic literature and research, even till the late 90s. Okay, so even beginning of the 2000s. Okay, we're still using things that happened back in the 1950s, combined all the way to that point. Okay, it makes sense. Okay, it works well empirically. Okay, but you have to think about it. Is what I found is interesting is at that time it's not enough data. Okay, don't have enough data, so you have to do ad hoc stuff. When it's ad hoc, it's a bit complicated, but there's nothing we optimize it for. Okay, it's just basically run it, do it, and then see how it works. Okay, there's nothing, no objective function, no loss function that we're optimizing anything for anything. Okay, so it's a matter of how do I reassign probability mass around all the words I've seen. Okay, and a lot of these are intuition. Okay, plug this in, do this in, and it works. Okay, and even back beginning of 2000, that's still nowadays because we started scrapping so much data from online. You have the computing resource that can do things. The N right now become very complicated. Okay, if you do a transformer structure, so they can encode more than n-grams, so that language model ability start to improve quite a lot. So you see less of this discounting, smoothing issue in the current modern language model. Okay, but if you go back into ASR, you still will see this thing. Okay, because in the ASR system, you don't usually have a very heavy language model to plug in. You need to do real-time decoding all those things. So the language model from n-grams still very prevalent in terms of automatic speech recognition. It is not as important for language processing, okay? Because if you're doing, language processing, you can wait, okay? In speech processing, you usually can't wait. You have to speak and it directly recognize those things. Okay? So that's another thing to keep in mind. Okay, some of the last things I want to say. Okay, assign probably the good stuff is what we really want to do. So seeing n-grams have okay probability, unseeing n-grams have get not so good probabilities. So we basically assign low probability to the best stuff. So again, these are trigram model, 20 billion word of Wall Street Journal. Okay. So last thing I want to talk about is think about this process, right? So how do we evaluate LLMs outside of ASR? How do we evaluate acoustic model outside of ASR? We talk about the ASR metric, okay, but then you think about when we learn automatic speech recognition, the acoustic model, video Markov model, we're learning maximum likelihood estimation of the parameter. So we're gonna say, okay, sound, okay, I get a bunch of this parameter tells you most likely parameter that will generate that okay. The language model, okay, I say, okay, I make assumption, word sequence is based on first order or second order Markov process, okay. I can assign a parameter to a point where it's most likely generated the text I've seen, okay, that's called n-gram model. But ASR system, okay, ASR system, the purpose is taking acoustic sound into a set of symbols, okay. The metric will talk about that. So these two are not perfectly aligned, okay. So by optimizing those things doesn't directly optimizing the automatic speech recognition system. So the word error rate, okay, is the most popular evaluation measure for automatic speech recognition system, okay. So because of the problem is ASR is a sequence, right? Sequence of acoustic feature to a sequence of symbol, right? Meaning word mapping, okay. So there are three kinds of error that could occur, right? Out of all the words in a sentence, at the random place you may insert a word that's not there as an error, okay. The place where there originally is a word but you don't have a word, that's called deletion, okay. A place there's a word but you use another word to replace that word, it's called substitution, okay. So for an ASR system, the word error rate is these three things combined, okay. When you think about training acoustic model, training language model, we're not training on word error rate. We're training on maximum likelihood estimation of acoustic model. We're training on maximum likelihood estimation of the n-gram language model. Okay. So how do we know the language model? If you have 5 different language models, 7 different language models, okay, or 2 other acoustic models, how do I know which one is best? Okay, the easiest one is run everything all the way through until you hit the WER, okay, word error rate. Okay. But this is a large effort, right? Because you have hundreds of hours of training, decoding, eventually get this number. Okay, so there are some ways you can do a proxy estimation of some metric, okay, to do acoustic model and language model selections. Okay, so again here repeat, right? Okay, so the reference is here now. Okay, hypothesis the thing the dog is here now, the all bark is now. Okay, so the word array can actually be over 100%. Because there are multiple errors that's happening, okay? And then the shorter your sentences is, the higher your word error rate is, okay? Because the numerator here is number of words in the utterances, okay, right? So word error rate can be quite large. Okay, I wanna skip here, it's okay. You also can get a feel of the word error rate. So the top is 0%, this is 13%, this is 35%. Okay, so we can kind of look at them briefly, get a feel of. Usually you see this thing at 0%. Of course, it's just transcript. It's the label ground truth. 30% is quite good. Okay, humans are about 5 to 6%. Okay, 30% is quite good. 30 by 30% or 20 something to 30%, you look at the output, you know it's trying to do recognition. Okay, it's doing okay, not bad, but you won't take it as your usage. Okay, over 50% of our receiver, you look at it and say it's doing nonsense, right? It's not generating stuff. It can be over 100% and so on. So this get a feel, okay? Because but if you try to compare between 13% to 14%, actually can't really tell. Okay, so usually it's more of a category. Okay, so people do compete on the absolute word rate, right? Some people get 5.6 and 5.5 or even 4.9, right? That little percentage of difference really, in terms of humans' consumptions of text, really makes no difference anymore. Okay, but the broadly, this single-digit word rate, sort of 10+% word rate, sort of 13-something% word rate. You can look at it, and if you run your system, you get some output like this. You can get a feel. Right, 15.5%, 16.9%. Right, it's very difficult nowadays to tell. Okay, which one is 15.5, 16.9%? You can actually look at your notes and try to guess yourself. Okay, it's really from our eyes perceptually, it makes very little difference between 1 point differences. Okay. So, anyways, want to say another thing is this acoustic model weight. So, in a iterary decoding, we have this language model multiplied by acoustic model. Okay. Sometimes they'll add a alpha here. Okay, trying to the regularize sort of AM approaches. So the AM probability can be dramatically overtrained. Okay, so you can tune that alpha. Okay, so so that it either discount more of that probability. Okay, and when you discount more, it practically give more weight to the prior distribution. Okay, so here's another sort of parameter you actually can tune. Okay, when you're trying to learn your ASR system. Okay, it's that probability weight. Okay, so those P of A of T, right? Those probability weight give it a parameter here. Okay, they multiply by the actual probability coming out from the word sequence. Okay, so you basically want to lower this into the similar range of the probability of the language, okay, so that they can actually regularize each other. Okay, otherwise, it's going to be dominated by either this one or this one. Okay, so that's a sort of regularizing parameter you can use to regularize your ASR system decoding. Okay, so there's this is a plot where you can tune that parameter and you see the word error rate differences. There's always a sweet spot where not too little is bad, too much is bad. Okay, somewhere in the middle is the proper way for big databases. So another last thing I want to talk about is evaluating language model. The best way to evaluate language model is an n-gram, at 2 gram, 3 gram. Okay, 5 databases. Okay, or you pull databases together, or you train on one single database. Each one will give you a language model. Which one is the best for your ASR scenario? And the best way, of course, you plug into the ASR system, you measure the word rate, okay, but then that means you need an ASR system, okay, and also the result depends on your acoustic model, how well it's trained, okay, so it becomes very confounded, okay, you don't know whether your language model is good or bad, okay? It's painful to compute, you also need to tune that AM weight, okay, because you don't know whether the regularizing effect between the AM and the language model, these two things, how they compete with each other. So you want this alpha parameter to be tuned. So too many things to tune before you can actually get that word error rate. So you don't know whether the effect of that word rate is coming from the language model or not. Okay, so there is something cheaper that can predict the WER. So there's a metric called perplexity. Okay, this is what we call the geometric average of the word probability. So P of average, average of per word probability. I from 1 to L plus 1, the probability of Wi given Wi minus 2, Wi minus 1 to the 1 over L plus 1 power. Okay, this is a geometric mean of the kind of this language model, all the words probability, all these trigram probabilities. Then inverted, so 1 over P of A average, so we call it perplexity. Okay. So if perplexity is high, okay, then there's a branching factors of the search space. Okay, so for example, if you have uniform unigram ln over k words, your perplexity equals to k. Okay, so every time there are k different options, okay, you can choose from. Okay, so that's what I call perplexity. So the perplexity low, that means branching factor is limited. So that means every possible next word branches is not too many. Okay, if it's very large, okay, then then that's not good. So anything that's non-uniform, okay, non-uniform universal language model will have a perplexity that's less than k. Okay, because the perplexity equal to k is the largest. Okay, every word is equally likely than each other. So the probability of every word that is equally likely to each other. So then as we decode, everything is equally possible. So that's what we call a branching factor. So there are k different ways to choose to the next word. That means you're not relying on your model anyways. It's a random guess. Okay, so because all the words are equally likely. So what counts on the next word, you just randomly pick one of the k. So there are k different ways you can split, okay, for the next word. So if you have well-trained language model, this should be lower. Okay, so there are less confusion, okay, of your branch, okay, because the next word can happen not equally likely, okay, because I already know from the back of my data sets, okay, these are more likely events that will occur. So we call perplexity is a good metric, okay, for the measure of AI, for the measure of the language model. Get this thing. So because there's a LM called perplexity, right? So that is coming from because there's a measure called perplexity. So they name the old solution called perplexity. Okay, so that comes from they're doing a geometric mean of their probability counts as the language stuff, and then in a way that they develop their large language model. Same thing. That perplexity is coming from the intuition of this perplexity. Okay, so you can do this thing by probability of I hate to watch, right? So then you have, that's the probability. So the average probability of just this thing, right? You have multiplied this into the 1 over L plus 1. So it's 3.059 10 to the minus 11 to the 1 over 5th, right? That's 0.00789. So 1 over that is 126.8. Okay, so the branching factor is this thing. So if you have another model, right? If you have another language model, you plug in, here you have another set of probability. You can compare average perplexity across the data sets. Okay, you want to choose the one that gives you the lower perplexity. Okay, so you want to choose the one that gives you the higher of this thing, higher geometric means of the probability. So it gives you a more on average descriptions about the likely word sequence. Okay, you want to pick a model that way. Then you do an inverse of that, right? It gives you a perplexity. So how branching factor it could involve. So you want the branching factor to be small, to be the right language model. Okay, so here's the thing. Okay, machine. Okay, Brown data sets is 600 million words. Here's our Wall Street Journal 23 million words. The perplexity of this is about 790, and then the ASL Wall Street Journal is about 120. Okay, so again, the perplexity also depends on the data sets. Okay, so there's some data sets there are just more ways the words are being put together, right? So if you write journals, novels, and those things, right? If you're reporting news, right, the branching factor is not that much. Okay, so 120 only. So the perplexity measure also depends on the data sources. Okay. So if we're using perplexity measure as a way to predict word error rate, right? You say, okay, perplexity measure I'm going to use, and then try to evaluate whether my LM is good for the ASR system. You cannot do it across different types of language models. So if you have word language model, you have classic language model, but you can't compare these two. But you have the same kind of language model, you train differently, and then you can compare. But you have a different kind of language model, you cannot compare with respect to each other. Then also you can do okay with a similar LM type rearing, training set, model order, pruning, all these different parameters you can choose to train your same language model. Then you can compare them, okay? But you cannot compare different language models using the representation. Okay, the log of PV, okay, with the word array, it actually fits quite well. Okay, given the data sets, given the same kind of language model, okay, the perplexity and the language model actually actually fits quite well. Okay, so intuitive, again, repeat, language model regularize the space, the search space of the acoustic model. The perplexity measure tells you how regularization how much effort it actually enforces that, right? So if the branching factor is small, that means there are not many ways your acoustic model can jump around. Because there are not many ways my next word or even my current word can branch out. Okay, so this kind of branching factor, if it's lower, then there will be less confusion. You regularize the acoustic model. It makes that entire Viterbi decoding search space more clear, okay, because there are only certain paths that it can actually go through, okay, not through every path, there's a certain path, right? Think about 128, that means that every time going to the next time slot, or I'm sitting here, coming to here, there are about 120 ways I can come here, not a million ways. If you have a million words that jump into you, okay, so that's that kind of branching factor really constrained, and also making sure acoustic model don't go all over the board, okay, to make sure as I decode through this very large ASR Viterbi decoding process actually works, okay. So language model perplexity provides a regularized way of doing Viterbi decoding on the speech recognition system. Okay, recap. So we need AM weight for a language model to have full effect because AM probability tends to be larger than LM probability. Okay, it's best to evaluate LM over WER, but perplexity measure itself also can be informative. It's cheaper to compute. Okay, because all you need is basically compute the utterances probability, take the geometric mean, sum of all those things, and then take a reciprocal, and you get the perplexity measure. Right. So of course, you think about any problem with word array, take that back home, right? To think about these are all standard ways people do things. We haven't get rid of word array, we're still there, okay? But word array has its own problem in terms of measuring, okay, how good a transcription is, because if you look at a 15.5 and 16.9 word array, just see your eyes, you don't see the difference, okay? So what that means about word array in terms of absolute measure, okay? It's actually a tricky objective measure. Okay? But we don't have any bad thing yet. Okay, so we'll still stick to word rate as the objective measure. Okay. All right, smoothing. A little bit recap. Lots of smoothing algorithm. We don't have time to talk about newer algorithm, but I think this one will set the tone of the modern ASR. Okay, those cat smoothing. Okay. Doing grouping estimate and also backup. Okay, even the newer discounting will build upon basically this kind of idea. Okay, like I said, the newer algorithm improved about 1% word rate over what people already know back in the 1980s, the CAS algorithm that we teach today. Okay, so all the development in the current century, okay, with the language model has very little improvement on the word array, but of course it's very difficult. Okay, once you get the system work so well, improving 1%, it's a very difficult task. But adding all those new tricks doesn't necessarily help improve quite a lot. Okay, so don't need to worry about model too big. Okay, usually with smoothing you can go with very high order of n. Okay, so Google back in the days would release, prior to this kind of large language model, they will release 5 grams, 6 grams, 7 grams language model, okay, just for automatic speech recognition community to use it, okay, because they have Google, right? So they have all these data set, they can train, okay, they have all these smoothing algorithms, they just train. So now they have this. So when they train the new language model, it's also not difficult because they have the data sets already back in the days. They keep continuing get the data from online, so they can get also very good large language model nowadays. But with the data source they have already in. So anyways, smoothing helps. Okay, get rid of the zero count problems. Build a language model. There are multiple ways. Okay, Kaldi has one. Okay, if you want to build your own language model, ASR-LM is a very good toolkit. Okay, it's written. The problem with language model, it's simple. Difficult to implement if you want to implement it fast, okay? Because it involves millions of word counting, okay? So think about if you were like me writing this, there'll be a lot of for loops, and then that thing will never finish in like months. Okay, so you have to have somebody sit down and actually find a way to speed up. Okay, all this counting business. How do we count really fast with millions of documents? Okay, so they usually just there's some people that are engineering genius. They just put together and release the toolkit, and you can use whatever you like. Okay, and then it has all kinds of toolkits that embedded. And SRM also has been combined with Kelly, so you can also those toolkits can also be combined. And then these two things put together, you get a working ASR system. If you have enough data, say over 200-300 hours of data with SRM and Kelly, you can actually get a commercially working grade ASR system directly. Okay, so those toolkits, they're not general toolkit. If you actually look into the way they write things, it's very highly engineered. So very fast, very quick, very well designed. Okay, so almost like a commercial system, but they are open source, which is I think helps the entire speech community to actually work out all these details. So the math looks complicated, but not too complicated. Okay, implementation. Okay, when I say HMM, right, it's implementation. Boils down math complicated, but when you convert, it's like five equations to learn HMM parameters. Language model looks complicated, but eventually it runs down to a lot of counting and then do normalization and all that's it. Okay, so what's really left is having the right toolkit, okay, to help you, because otherwise you don't have nowhere to start. You cannot write all these things by hand from scratch. It takes too much time, okay, and then it doesn't work anyway. So you have to have a group of people writing all these things together. So SRM and counting toolkits are two toolkits. I think once you've learned, you should be very up to the speed with the current ASR system and understand language model. The role of language model is in-depth virtually connected word recognition. When I'm transiting from other word to this current word, I want to look at whether I stay in the same word or have transited from the other word. That probability, which one is largest, that probability will depend on the observation. Also, POV given WQ. POV given WQ is a language model, and that being put in together to the whole vector-based coding. Okay, so again, so the scheme itself is still vector-based coding. A language model is a component. Okay? Acoustic model is another component. Okay? And these things are being combined to find the best word sequence. Okay, so keep all these things. See what I have left to talk about here. Yes, it's a lot of data. Yeah, so here's a plot. If you have more and more data, the word rate always drops. Okay, so that's it. Okay, so I think we'll stop here. That's a brief overview on the language model. Remember the Ingram language model? Basically taking a first order, second order Markov assumption, like we do the acoustic model. We do first order Markov assumption on the progression of the MSCC. To make it a hidden Markov model. Here, the word sequence model will assume this is an n-gram, okay, sort of sequence model. Okay, when we put all these things together, and perform a inference called finding the maximum word state sequence given observation, and that finding the maximum over a sequence, that kind of process is called vector-based coding. Okay, so again, you just have these three things being put together. Okay. To form the modern ASR system to do speech recognition。好，我们先到这里，我们下次再来做个整体复习。